So what we have here is a simple circuit with a battery and a resistor and a capacitor connected in series. So we say series RC circuit. Initially, the capacitor is uncharged, okay, no charge on the capacitor. So when you close the switch, there's a switch here, then we say that is at time t equal to 0, we start our timer at t equal to 0. You will observe this is happening. If you plot a graph of charge against the time, the charge will gradually increase. This is the charge on the capacitor. It will not come to its maximum value at once. It will be charging slowly. So an electron will come, stop here, so this side become negative, and an electron will leave, feeling the repulsion, this will become positive. So it just keeps happening. Slowly the charge will build up, and it will be a curve like this, the building up of the charges. At the end, the charge will reach a maximum value. When that happens, we call it charge Q, and the potential difference across the capacitor will be the same as the EMF of the battery. So when that happens, the charging will stop because the battery is sending current in one direction and the capacitor has its polarity reversed, the positive here, the positive there. So it is trying to send the current in the other direction. And when the potential difference across the capacitor also becomes equal to the EMF of the battery, the charging will stop. There will be no more current. So this is the line that describes the charging of the capacitor. It will start with a zero charge and gradually increase and reach this value at the end. Where the potential difference across the capacitor is also the EMF of the battery. And we observe that this charge versus time follow this equation. Okay, where R and C is the resistance and capacitance of the capacitor, T is at a certain point in time. So this small q is the charge on the capacitor at that point in time, the charge as a function of time. And we can show very easily using this equation. If we take this equation to correctly describe this line, at a time equal to RC, given by the product of the two values, the resistance value and the capacitance value, it has a special name. We call it the time constant, and we denote the symbol tau for this time constant. So it's an important concept in RC circuit. Okay, you should know what we mean by the time constant. It is equal to the product of the resistance to the capacitance. At that time, what happens if we substitute here T equal to RC, you will see the charge will be equal to the maximum charge it will eventually reach. 1 minus, this is RC and RC, it will become 1, so minus 1. If I calculate this value, it will be 0.632. The E is the natural logarithm base, right? It's called the Napier's constant. So it is 0.632. So at the time of one time constant, the charge will reach 0.632 times the maximum charge. Or you can say it will reach 63.2% of the maximum charge, the saturated charge. So that's how we define the time constant of in a RC circuit. So you should know this word time constant, so you now understand what it means. And also you understand that the at one time constant, the charge will reach 63.2% of the maximum charge. Okay, so that is all there in this slide. Let me move to the next slide. At the beginning, the capacitor will have no charge on it, so you will have the maximum current. There will be, if you draw current versus time, it will be different from the charge versus time. At the beginning, the current will be its maximum current. So as the charge is being built up and the capacitor become also like a voltage source trying to send the current in the opposite direction, the current then will decrease and it will look like this. So don't confuse. Now what we had before is the charge against the time, charge on the capacitor against time. That is like this. Current against the time will be the opposite direction. It will start with a big current and it will decrease exponentially. So when the circuit is completed by closing the switch, the capacitor will start to charge and the capacitor will continue to charge until it reaches the maximum value given by this. Once it is fully charged, then the current becomes zero. The fully charged will, take time to happen. In fact, now, if I go back to our equation, let me derive some equations. This is, I started with, the charge at any time t is given by this equation, and we call this value r into c as the time constant, and we use the symbol tau, Greek letter tau. We use the same symbol for the torque also, but don't confuse that with that. That is in mechanics. Now we are in electricity. In an RC circuit, we define something called time constant. It is equal to the product of the resistance with the capacitor. And we use the symbol tau, the Greek letter tau, to denote the time constant. Then we can continue to get an expression for the potential difference across the capacitor as that with the time. All I do is just get this equation from the definition of the capacitance, Q is equal to C delta V, and we call this maximum charge that it gets eventually as Q. Then we substitute for the maximum charge and the small q here in terms of the delta V and the CE. Then what happens, the C will cancel with C, then we have this equation for the potential difference as a function of time. This is while charging the capacitor. Then we continue, then we apply the, what do you call, the Kirchhoff's law, the loop rule to the circuit, then we can get an expression for that current as well. So the current at any time t will be given by this equation. So you see there are three equations that we need to worry about, right? One for the charge as a function of time, one for the potential difference across the capacitor as a function of time, and one for the current in the circuit as a function of time. So these three equations applied for charging a capacitor. Now we do another thing. We charge a capacitor with a battery, then we will discharge. But before I go to that, I have to cover this slide. This slide tells you about certain property of a RC circuit. If the time constant is large, if tau is a big number, then what we can infer from that is if tau is large, it will take long time to charge it, obviously. Because tau is the time it takes for the charge in the capacitor to get the value of 63.2% of the maximum charge. So if the tau is large, it will charge slowly. It will take longer time. If it is small, then it will charge quickly, faster. However, you don't have to wait too long to get it completely charged. Theoretically, we have to wait infinite time, right? Wait forever. Infinite time in. So only at t is equal to infinity, the q will become capital Q. But you don't have to do that, because if I substitute t is equal to 10 times the time constant, which will be a reasonable time, not a large time. If you substitute in the equation, it becomes almost the fully charged. It's 99.99% of the full charge. And that's good enough. For all practical purpose, we can say the capacitor in the RC circuit will become fully charged after 10 times the time constant, which will not be that much. It's not infinity, of course. Right. Now discharging. So finish with the charging, discharging. What do you mean by discharging? We get the capacitor fully charged, let's say by connecting to the battery. Let's say it is fully charged, or charged somewhat, doesn't matter. Then, say we get the voltage, let's say it has a certain initial voltage of delta V0, and we connect it to a resistor and a switch as well, so we don't connect it immediately. What will happen now? Is there a battery to charge the capacitor? No. It's only the capacitor. It is going to neutralize itself because there is a positive charge here. It will flow and come and neutralize this. So there will be a current through this circuit, not forever, because one by one the charges will get neutralized and eventually the charge will become zero. This is discharging. So note that we are discharging the capacitor. So at the beginning there will be a certain charge given by C delta V 0. Then the charge will become less and less with time, and theoretically it will come to zero charge only at infinity, but again the same thing, if you wait for certain 10 times the time constant, it will become almost zero. But here it's the same time constant. The time constant will be R into C. The equation is this. Now, don't confuse equation, right? We had a different equation for the charge when it is charging. It was like this. This is the equation when charging. But when discharging, there is no 1 minus. The Q as a function of time, it is not increase, it is decreasing. The charge will drop as you wait. As the time increases, the charge will become less and less and less, and we can eventually become zero. So this is the equation for the charge as a function of time when discharging. So do not confuse that with this equation. That equation is when we are charging. And same constant appears. This tau is the RC. So it is the same thing. Now what happened? If you wait one time constant, equal to the RC, the charge will decrease from its initial value to 36.8% of that initial value after one time constant. After one time constant. So we can also put it in different way. I can say Q become 36.8% of the initial Q, but you can also say it will be reduced. The initial charge will be reduced by 1 minus 36.8% from the initial value, which is equal to 63.2%. So you can put it in a different way. We can say after one time constant, the capacitor loses 63.2% of the initial charge. In other words, it reaches the value of 36.2% of the initial charge, 36.8% of the initial charge. Right, then we can continue. We can substitute Q in terms of the delta V and the initial charge in terms of the delta V0. Then the C will cancel both sides of this. Then you get this equation for the potential difference across the capacitor. So the potential difference also will decrease with time, exponentially decrease. And continuing, I can get an expression for the current as well. So the current saying the delta V over R, we'll substitute those from there. Then finally, we get this expression for the current at any time t like this. See, in all three cases, it is exponential decay. While discharging, charge decreases exponentially. potential difference decreases exponentially, and the current will also decrease exponentially. Right. So in this is a short section, okay, because we just have the simple RC circuit, and we have set of three equation, one for charging, one for discharging. They are different, okay, so you should not confuse between them. So we are ready to do a question. So we have an example problem here. What is this? An RC circuit. We have a capacitor and a resistor connected in series via the switch. Okay, it doesn't matter where the switch is. And of course, it is being charged by a battery. Initially, okay, this is very important. Initially, no charge on the capacitor. You close the switch, the capacitor will begin to charge. And this is charging question or discharging question? Charging question. So let me now go to the formula sheet. So you know what is in the formula sheet. This is the formula sheet, and this is all chapter 17. This is all chapter 18, and this is the section we are at, RC circuit. See, there are, as you can see, three equations for charging and three equations for discharging. Q as a function of time, that is a charge on the capacitor. Potential difference across the capacitor as a function of time, and the current as a function of time. Current in the circuit as a function of time. Then while discharging, we have different set of equations. They are not the same. You can see it very clearly. The Q as a function of time, this is discharging. This is the potential difference as a function of time. This is the current in the circuit as a function of time. Which equation should I pick? The question is asking us to find the current, and it is discharging, not discharging. So I should pick this equation, right? So already you don't have to derive it, you just have the equation, you just use it. Huh? I'm sorry. Hide. Okay, close this. Yeah, thank you. What happened? Maybe I went to the next slide. Okay, right. So, I mean, this is, you don't have to prove anything, okay, because we're going to get multiple choice exam. You will be given the formula sheet and the formulas are there. How can I ask you to prove it? You will not prove, you'll just go pick the equation. So just don't worry about this, how to prove. This is the equation, you pick it from the formula sheet. This is the I0. I0 is the potential. EMF of the battery divided by R, substitute, EMF of the battery is given, R is given, and you put what is the time. Did he give a number for us? No. He's saying when the time is exactly one time constant. So when you put here tau, which is equal to RC, RC will cancel with RC. So what you have is 1. So e to the power minus 1. Then you know how to calculate this. All right. Anyway, let me show you. I will take my calculator. Right. So this is a fraction, so I can use this guy. 7.62 come down, 60.4 come up, go up, multiply by, right. How do I get this e to the power? Not alpha, shift, right? Shift ln. It is actually ln inverse of the ln. Ln is the base e, right? Not base 10. So shift ln. You will get the e. Then you need a negative sign, right? I mean, it's very important you do not forget the negative sign, because in a rush, you will then you get the entirely wrong answer. It will not be able to calculate sometime. So negative sign, use this negative sign here. Okay. Then 1, you just put 1. Equal. Now, this is not a solving equation, it's just calculating the whole thing. Press the equal button, 0.04. So that is it, right? So, number 20. So we have a capacitor. Let me read the question. For the circuit shown in the figure, the switch is initially open and the capacitor is charged already, and its voltage is 22.5 volt. So that much charged. The switch is then closed at time t equal to 0, and the capacitance of the capacitor is 0.330 farad, and it is start discharging. When you close the switch, is there a battery here? No. So what happened? The capacitor will discharge through this capacitor. Then he is asking, what is the current through the circuit immediately after the circuit is closed at t is equal to 0 at the beginning, that means. So, this answer is you don't even have to use the equation, because the initially the current will be, even if you look at the equation, now is it charging or discharging? Discharging. So the equation you have to pick from the discharging section. So the current for the equation for the current is this. Don't pick from the wrong one, okay? This is, maybe this is written as tau. This is the equation. Discharging, okay? If it is charging, it will be 1 minus, but it is now discharging. So this is the initial current, t equal to 0. If you put 0 here, e to the power 0 is what? 1. Okay. So initial current is, we already know the expression. Initial current is E, EMF of the battery divided by the R. So even without knowing the equation, you know that for a fact. The initial current will be at the beginning, the capacitor has at the beginning, right? The capacitor will be fully charged, delta V0. I mean, I prefer not to write E, because there's no battery. I shouldn't be writing. It will be delta V0. Okay, I shouldn't write. There's no E to talk about. We already took the attendance. You're late. No, you're not here. How can you say it's not here? I took the attendance. I called. Then why did you sit over there? You should. If you are sitting there, you are not present. You are sitting in front of me. I should see you are not present. You came only now. So it's not E, it is delta V0, the initial voltage. Substitute, get the answer. Delta V0 is 22.5 and R is 1500. Somebody tell me the answer. 15 milliamperes, right? Maybe you will get in amperes. What did you get exactly? It's SI 0.015. So answers are in milliamperes. You divide by 1000, you will get 50 milliamperes. Question 21. The same circuit, actually I told you before, it's one question broken into 3 questions, so you score at least 2 of the 3 questions. This is an easy one. Just simply, all these things doesn't matter. I have the circuit, but the time constant. So it doesn't depend on what's going on. For the time constant, all you need is the value of R and the value of C. So time constant is equal to R into C. R is equal to 1500. Make sure you put that in ohms, okay? Ohms is the SI unit for resistance. And C is 0.0330. Farad is the, not microfarad, farad is the SI unit for capacitance. So can somebody tell me the answer? B. Please don't make mistake. If I don't remember the answer, I hope it is correct. Okay, right. Now let's go to number 22. Same thing, right? Same thing. What's the question? Now this time he is asking about the voltage across the capacitor. So he's asking how long after, because start with the voltage of 22.5, same as before. What is the potential difference across the capacitor when the time is, no. If the potential difference becomes 20 volt after some time, at what time that does that happen? Right? What is the equation I should get? In the discharging section, the equation for potential difference. So that's the equation. Just, even if you forget, no problem. You go there and pick the equation. Now all you have to do is to substitute. What is delta V? 20. That is, usually you ask for delta V at a certain time, right? But now it is reversed. You are giving the potential difference and asking us at what time that happens. So since we can use, you don't have to do any manipulation of the equation, algebra, anything, because you are using a calculator which can solve equations, so we are safe. T is the unknown, so you will put it as X, right, in the calculator. RC, actually the previous question we calculated RC. It doesn't matter, you can ignore that because it may be a different value. So you put the values of R and C. R is what? 1,500 and C is 0.330. Okay. Take your calculator, write the equation in the calculator and tell the calculator to solve it for you. Equal, don't do this, right? You need the symbol, the sign alpha equal 22.5 multiplied by E. How do you get E? Shift len, negative sign, then you put the fraction. So T, you will write alpha, right bracket, X. Bring it down, R into C. R is 1,500 multiplied by C is 0.33. That's it. Otherwise what you have to do, you have to take the inverse in both sides of the equation. You have to solve for that and bring the T is equal to something. Then you don't have to do all that. You can use this solving mode in the calculator. You're allowed to bring your calculator and just solve it. How do you solve it? Shift calc. Is this the answer? No, actually it is the answer because I did this in my previous class. Okay, so but that's not the answer. You should see, press the equal button again. You should see X equal to something and the L minus R equal to 0. Then you know it has calculated. The answer is 58.3. So B again. Right.